Okay, hello and welcome. This is SFU Math 232. It's Brenda. We're now in section 4.2, Properties of the Determinant. The determinant actually has a lot of interesting properties associated with it, and sometimes actually surprising properties where you can do things where you think, wow, that's surprising that happens. So we're going to take a look at some of those properties in this lecture. And then one thing you should take away from this is that if you're going to be trying to determine a determinant, there's many different things you can do, and sometimes doing it one way is much quicker than another, and in terms of using the properties to simplify the calculation. Because as we saw, if you just go for the cofactor expansion, the computations on that grow as n factorial, making it not just infeasible for you to do by hand, but actually infeasible to just do a brute force approach with a computer either if the matrix gets large. Okay, O(n) factorial is to be avoided at all costs. Okay, so let's take a look at what happens to the determinant when we do some elementary row operations. So the first thing to notice, our first property here, is that the determinant of the transpose is the same as the determinant of the regular matrix. So you can, this can be proved by induction and cofactor expansion. That is done in the textbook. Let me just refer you to the page. That is page 190 if you want to check through that proof. I always recommend checking through the proofs because it does give you some practice and you get an understanding of why things must be true. Let us just do a 2x2 example just to sort of see this in action. It's fairly straightforward. Also just remind us how to calculate a 2x2 determinant. So here's a 2x2 example. So we'll take a matrix A. It is 1, 2, 3, and 4. And then we'll take the transpose of that matrix. That will look like this: 1, 2, 3, 4. The rows and columns have been exchanged. And then we'll calculate out here determinant of A. That would be 1 times 4 minus 2 times 3. And that gets minus 2. And here I'll take the determinant of A transpose. And that would get me 1 times 4 minus 3 times 2. I mean, the 1 times 4 is the same, and of course the 3 and the 2 have been exchanged, but regular multiplication commutes, so then this is also minus 2. Okay, so you could just do this in the general case. So try that yourself. I mean, here's the general 2x2 matrix, A, B, C, D. Take the transpose, take the determinant of both of them. You'll see that for at least then you'll have proved it in the 2x2 case. And then you can see how you could do this via induction, because all the cases are going to eventually come down to doing a 2x2 determinant after you've done the cofactor expansion. Okay, there is a major consequence of this, and that is the rules for determinants which hold for rows also hold for columns. Because basically what you can think of it is if you prove some rule that is true, if I do something to a row, I determine how I change the determinant. Then if I wanted to do a similar thing to the column, all I'd have to do is take the transpose, then the column would then be a row, the rule would apply, and then I would take the transpose and go back. And we've just seen that the transpose does not change the determinant. So really the main point, I think, of this determinant of A transpose is determinant of A is that column and row operations are equivalent in terms of what we're allowed to do, and determinant will or will not change. Okay, so let's get our first set of rules that is happening. So if we make a matrix B from A by multiplying a single row, and that's why this column is here. So if it applies to a row, it applies to a column. So I'm just going to not read that, but this is always going to be true. So if we multiply a single row by a scalar k, then the determinant of the new matrix is k times the determinant of the old one. If we exchange two rows, then the determinant becomes multiplied by minus 1. And if we produce a matrix B from A by adding a multiple of one row to another row, then the determinant is unchanged. So row up, like those operations, like row 2 becomes row 2 plus 3 row 1, those operations do not change the determinant. Okay, so it's a theorem. A and B are proved in our textbook. So A and B proved in the text. I would also say take a look at page 195, P2, for a hint on C, for a hint on proving C. It's actually an exercise in the textbook. It might be a valid thing to, I think it is a valid thing to try. It's a good thing to try. Let me just say I'm not going to prove C, but I'm going to just take a look at a numeric example to get a sense of why it's true. So this is a good strategy anyhow. Like say you're thinking to yourself, wow, I see a statement here, supposed to be true. I'm going to try to prove it. Sometimes just looking at a couple of examples and seeing what happens with the numbers leads you to be able to formulate what happens in the general case and construct a proof. So let us just take a look at a 2x2 example and get a sense of why it's true. So I'm going to take my famous matrix: 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and what I'm going to do is compute the determinant of this. So I have that sitting there. So the determinant of A. So I'm going to use cofactor expansion along the first row. So that determinant looks like this: 1 times the determinant of 5, 6, 8, 9. That is the submatrix formed by crossing out the row and column that contains that element 1 in it, and then minus 2. Remember, the sign changes as we go across. We cross out the row and column containing 2, and we get 4, 6, 7, 9. And then we go across again, and we cross out the row and column that contains the 3, and we get 4, 5, 6. Sorry, what am I saying? 4, 5, 7, 8. 4, 5, 7, 8. Okay, so we have now the determinant of A written this way. Now I'm going to form B, and I'm going to take B. Okay, what am I going to do? I'm going to do a row operation. I'm going to take row 1 becomes row 1 plus 2 row 2. Okay, that is going to be B. And then I am going to I'm going to write it like this, actually. Let me just go ahead and write it. So B is going to be this matrix. Row 1 is going to change. It's going to be itself plus 2 times row 2. So I'm going to take this entry will be 1 plus 2 times 4. I'm going to leave them like this too, so that I can get a sense of what's going on. So this one will be 2 plus 2 times 5, and then this one will be 3 plus 2 times 6, like that. And then the other rows I'm leaving unchanged. So that's my new matrix B. Okay, now what I'm going to do is write out the determinant of B using cofactor expansion along the first row. So that then looks like this: 1 plus 2 times 4 times the determinant, this 5, 6, 8, 9. These submatrices are going to be exactly the same because I'm going along the same row, and the other two rows have not changed. Four, 6, 7, 9, and some brackets there. And okay, so our claim is that determinant A is equal to determinant B. Okay, so the first thing I'm going to notice is if I look here, I have the determinant of A sitting right here, like this guy times this minus this guy times this plus this guy times this. That is exactly this. Okay, so that means that for this statement to be true, these other guys have to be equal to 0. So the other 3 products have to be equal to 0. So I'm saying that this product, that 2 times 4 times the determinant of this, 2 times 5 times the determinant of that, and that times the determinant of that have to be equal to 0 if these two things are going to be equal to 0. So if det A is going to be equal to det B. So I'm just going to take a look at what happens here. So I'm going to put 2 times 4, and I'm going to compute the determinant of this. Okay, I'm expecting this to come out to be 0. And then I'm going to sort of just take a look at why it does come out to be 0. Then you guys can try and generalize this, use the hint in the textbook, and see if you can come up with a proof for this. Undoubtedly, you could look this up too after trying for a while. If you don't come up with anything, then take a look it up on the internet, and you'll no doubt be able to find it somewhere, and then observe what you didn't see or how the person has gone about it. Okay, minus 5 times 7. Okay, now I'm going to look at this series of products added together and ask, are they 0? And so I'm going to say, okay, here I see the very first one, 2 times 4 times 5 times 9. I'm thinking of this here, 2 times 4 times 5 times 9. So 2 times 4 times, I see the same thing right here, 2 times 4 times 5 times 9, and it's negative. So that thing cancels out. And then I look at the next one. Let's look at another one. 2 times 4 times 6 times 8, and it's negative. So now I'm thinking 2 times 4 times 6 times 8. And then I look, oh, do I find that anywhere? 2 times 4, yes, right here. 2 times 4 times 6 times 8. So that one disappears. And then there's just one left. Let's think here. We've then got 2 times 5 times 6 times 7. So we got 2 times 5 times 6 times 7. And then here we have, and that's positive. And then here we have 2 times 5 times 6 times 7 negative. So that indeed, this thing indeed is equal to 0. And then the rest of it is just sitting there. So indeed, in this case, we've shown that this row operation did not change the determinant. We can maybe see how this is happening. It's kind of cool, actually, because the numbers are combining in this way that that is, I think, not obvious without like going through a detailed example. Okay, so that's the effect of the elementary row operations on the determinant. Okay, so let's look at a couple of consequences of this. If A has 2 identical rows, then the determinant is 0. So you definitely want to notice that if you're calculating a determinant. If one row is a multiple of another, then the determinant is also 0. And the determinant of k times A is k to the n times the determinant of A. Okay, this is multiplying the entire matrix by k, not just a single row. Okay, so let's just look at a couple of proofs. Might be a bit of an exaggeration, but we'll just sketch out why these have to be true. So let's take a look at A. Okay, we know already from the previous theorem that if we exchange 2 rows, det B equals det A. Okay, so we already have this from before. Exchange 2 rows. That implies that determinant of B then is equal to minus the determinant of A. If B is exactly like A, but with 2 rows switched. Now let's look at what happens if we have 2 identical rows. Okay, so I'm just going to run an example here so we can see what's going on, but this is true in general. Here's a matrix with 2 identical rows. Okay, so it has some determinant. So determinant of A is some number, C. Okay, now I'm going to switch row 1 and 2. Okay, of course it looks exactly the same. Switch row 1 and 2. Okay, that means that I have switched row 1 and 2. So I switched row 1 and 2. I mean, I end up like it's the same. So if I switch row 1 and 2, I still have A. But then because I've switched 2 rows, the determinant of A has got to be minus what it was before. So minus C has to be equal to C. And that means that C is 0. Okay, so the idea is that if you exchange 2 rows, the determinant changes sign. And if the 2 rows are the same, I mean, the determinant doesn't actually change. And then that means that yeah, like this, det A is minus det A. And that implies that that A is 0. Okay, all right, so there's that. Now, if we've got a multiple, one onto the other, we're just going to use what we did before. So we've got, and again, I'll just put an example here so we can sort of see what's going on. But if I have like this matrix here, where the row 2 is a multiple of row 1, it's twice row 1, like that. Okay, then I can factor that out. Like that. Okay, and then that means that I have multiplied one row by a constant k. So I know that, let me just call this matrix B. Yeah, so that is actually quite good. So B, keeping this thing equal to A, I'm going to call this thing here B. So the determinant of B is equal to 2 times the determinant of A, because I multiplied the row by one row by a constant, and we already determined the determinant of A is 0, so that is 0. Okay, so that is, again, just combining with something else we used just on the previous slide. Okay, the final one, the determinant of K times A, so that's every element in the matrix has been multiplied by K. That is equal to K times A. Did we see that before? We did, right? I'm just referring back. We saw that single row. This is also an incorrect statement. It's not how I want to write this down. What we saw is if we multiply a single row. Okay. We saw if, sorry about that, we multiply a single row by K, then the determinant is equal to K times det A. Okay, now what we're doing in this case now, we multiply n rows by K. So that means that the det of, this is a, this doesn't make sense really. I don't like the way I've wrote this. If we multiply a single row by K to get B, okay, then this is the case. Sorry, I don't want to make this looks kind of a false statement. Okay, so let me just write this. Determinant, then the determinant of B will be K times the determinant of A. That's a single row. Now we multiply n rows by K, say to get C. Let's just do it this way. To get some other matrix C, then I'm saying that the determinant of C, which is equal to the determinant of K times A, we're multiplying every row. So each time we multiply by a row, we get a factor of K appearing here, and there's n rows. So this is K to the n det A. Okay, just a Okay, so we're going to just now see these properties that we've got of the determinants to evaluate some bigger determinants relatively efficiently. And we're going to do this by hand. Clearly, computers are the way to go on this. Computers can do lots of calculations quickly, but we still need to realize that the problem needs to be done in a smart manner, because nobody will be evaluating on a computer determinants by brute force cofactor expansion. It takes up way too much, there's way too many calculations when the matrices get large. Okay, so here is a 4x4 matrix, which we are going to try to determine the determinant. Try to figure out what that is. Okay, so the idea I'm going to encourage you is, if you see something like this and you're going to be doing it by hand, go slow at the beginning and then start down the fastest path, remembering that 0 is an awesome number. Okay, so what am I going to do here? I'm going to recognize that the row operations do not change the determinant. So I'm looking here and I'm seeing this row, row 2 here has a 1 in this position right here. And I'm going to use that. I'm going to do 3 row operations. I'm going to take row 1. I'm going to replace row 1 with row 1 minus 2 row 2. I'm going to take row 3 and replace that with row 3 plus 2 row 2. And I'm going to take row 4 and replace that with row 4 minus 3 row 2. That the objective there is to get a 0 here, here, and here. That is my idea for these row operations. I'm going to do these row operations, and when I do that, this matrix is row. So these I get a row equivalent matrix, and it looks like this. Make all these calculations. Admittedly, it's hard to make all these calculations without making a small error. I had to do this one twice, and then I checked it with the computer. Okay. All right, so we do that, and then now what has happened is I have got a column where all of the entries except for one of them is 0. And then now I'm going to do the cofactor expansion on that column. So I'm going to recognize that this entry here, that is in a position where it's negative, so that I'm doing the cofactor expansion properly down that first column. So now the determinant can be written this way: minus 1 times the determinant of the that matrix, the numbers that are left there. That is 7 minus 5 minus 1 minus 2 5 7 6 minus 4 minus 5. I don't have to do any of the other ones because they're being multiplied by a 0. That's the genius of the 0. Okay, now I'm going to do exactly the same thing. I'm going to have to do cofactor expansion here, but instead of doing that directly, what I'm going to do is I'm going to use the fact that I've got a minus 1 right here, and I'm going to do column operations, because columns and rows are the same with respect to what they do to the determinant. So I'm going to do this. Column 1 is going to be replaced with column 1 plus 7 times column 3, and column 2 is going to be replaced with column 2 minus 5 times column 3. Okay, that gives me a new matrix to calculate the determinant of, and that looks like this: 0, 0, minus 1, 47, minus 37, minus 29, 21, and minus 5. And then I will do the cofactor expansion along this first row because of those 2 zeros. So I'll do the cofactor expansion along here, and that will give me, and then I see that that's plus, minus, plus. And so it's, and then, but the number is minus 1. I've got the minus from before, and try not to lose a minus 1 here, like that. And then what am I left with? I'm mercifully down to the 2 by 2 matrix, which I can now compute the determinant of, and that minus sign, these two things cancel, and so I am left here with 47 times 21 minus 30 times minus 29, and that, folks, comes out to 117. Okay, so that is, I think, probably faster than just going, I mean, there is no non-zeros. You might just think of going for the cofactor expansion right away. I think this is probably faster. Okay, let's just say a few things about matrices that have a special form. You always want to notice this. If you see upper, we saw this before, but if you, when we were looking at the elementary products, but if you see a 4 by 4 or any, it doesn't matter what size actually, n by n matrix, that's upper or lower triangular. So this one here is upper triangular, and this one here is lower triangular. Then the determinant is simply the the product of the elements on the diagonal. That's a very nice feature. Let's just, let's just do that. So the determinant, I'm going to call that matrix UT. For upper triangular, I'm going to do the cofactor expansion along the first column. So it's going to be then equal to A11. And then what's left, I'm crossing out those two. I get this A22, A23, A24, 0, A33, A34, 0, 0, A44. Okay, then I do the same thing. I do the cofactor expansion along here, and I get A11, A22, and then I'm down quickly down to my 2 by 2 case, and then I compute that, and I get A11, A22, and then A33 times A44, and then I don't have any, this is 0, so that other product is 0, and I'm done. So it is the elements along the diagonal. So just write out the same thing for the lower triangular. Exactly the same thing happens. You do the cofactor expansion along the first row. Okay. So triangular matrices are nice in terms of finding their determinant. It's very fast. Here it is stated as a theorem. The determinant of I is 1. Let's just take a look at I3, for example. That is 1, 0, 0, 0, 1, 0, 0, 0, 1. And we already seen this is upper and lower triangular. And so we can see that the determinant is 1. And it's not surprising that is for all of them. Okay. I'll just write that down. Okay. I am going to do what I think is maybe a bit of a painful example. It's actually painful working it out anyhow. I'm going to do this by reduction. I'm going to find this one by reduction to row echelon form. Why am I going to do that? Because if I reduce a matrix to row echelon form, I end up with an upper triangular matrix, and then I can just multiply the elements on the diagonal. Okay, so we already actually know the answer to this problem, but let's just go through doing it another way, and we get the same answer miraculously at the end. Okay, so I'm trying to take the determinant of this, and the first thing I'm going to do, let me just in fact do it right here. I'm going to I'm now sort of, yes, I'm taking the determinant, and what I'm going to do is when I do things that change the determinant, I'm going to keep track of those. But what I'm doing is the Gaussian elimination on the matrix. So my first step is going to swap rows 1 and 2. That is to move this 1 up here into the pivot position. Okay, so I'm going to swap those. When I swap 2 rows, that I have to multiply the determinant by -1. So I'm going to put that minus there for that reason. So I'm just swapping the 2 rows. And like that. And then I am going to, you can maybe treat this as a review of Gaussian elimination, or maybe you can stop the video and just do it yourself and then check your answer. So I want to get zeros all there. That's my next job. So I'm going to do that with these row operations. Row 2 is row 2 minus 2R1. At the same time, I can do row 3 is row 3 plus 2R1, and row 4 is row 4 minus 3R1. Okay, so then I perform those row operations, and row 1 was unchanged in this thing, and then I my 3 zeros there, and I get this 7 minus 2, 6, minus 5, 5, minus 4, minus 1, 7, minus 5. And then next in the Gaussian elimination is to make this guy here a 1. So to do that, I'm going to take R2 and I'm going to multiply by 1/7 R2. So I'm thinking of what I'm effectively doing is factoring out the 7. So I have to keep track. That does change my determinant. So I keep track of that in this manner here. This becomes -7. And then I perform the row operation. That is going to be 0. Now this is 1, and then that is minus 5/7. And I start to feel very unhappy because of the introduction of the fractions, but I forge ahead nevertheless. Okay. Okay, I am now here. All right, so next thing is I need to get the zeros in these two locations here. So I performed the row operations for that. That would be R3 is replaced by R3 plus 2R2, and R4 replaced by R4 minus 6R2. Okay, there's no change in the determinant when I do this, so I don't have to take account of that. So the key thing when you're doing this is, okay, I had to introduce this minus sign there, and then I had to introduce this 7 here. You mustn't lose those things, otherwise the answer will be incorrect. So these two operations here, though, do not change the determinant. So I keep going, and I start praying that I don't make an arithmetic mistake, and I got these numbers here. 0, 1. This row is not changing. And then I've got 0, 0, those are there. These two are going to, that was the purpose of the row operation. And in doing that, I got this 25/7 and 47/7 and 2/7 and minus 29/7. Okay. All right, so my next step in the Gaussian elimination here is to make this guy a 1. And in order to do that, I mean, I'm multiplying by 7/25, but thinking of this as I am factoring out the 25/7. So I have to make sure I keep account of that. So my row operation here is R3 is becoming 7/25 of R3. But I have to keep track of that in the determinant here, so I'm going to do this in red. So I still got that minus 7 there, but here I'm thinking of factoring out the 25/7 like that, and so then that is the effect on the determinant of multiplying a row by a constant. Okay, so the key thing is to have the right reciprocal. It's not 7/25, it's 25/7. So make sure you understand which of the two it is and why. Okay. All right, so I get that, and then that gets me, I'm going to write out the rest of my matrix here. I'm going to start being a bit lazy. I got this 1 minus 3, 2, 2. I know what's going to happen is I'm going to get down soon, and I will be multiplying together the elements on the main diagonal. Right? So I know this is a 0 and a 1. I don't actually care what's here or here anymore. This is going to be 0, 0. Now this is going to be a 1, and then this number is going to be 47/25, and then I've got 0, 0, 2/7 minus 29/7. Okay, we're getting close, folks. It's not much longer. No, and so I need a 0 in this position right here. I need the 0 right here. Okay, and in order to do that, I'm not going to bother to multiply and then do a row operation. I'm just going to immediately go for the row operation. I'm going to take row 4, and I'm going to replace it with row 4 minus, excuse me, 2/7 row 3. That does not change the determinant, and so I can proceed like that, and I will write this out, and then I will be almost at my answer. So that is going to, this is going to cancel here. So I'm left here with minus 25. And I've got this matrix minus, 1, minus 3, 2, 2. And then I've got 0, 1. And there's some numbers here which I no longer feel like copying out. Then there's this 0, 0, 1, and there's something here, and then I've got 0, 0, 0, and here I've got minus 29/7 minus 2/7 times 4/7 over 25. Okay, Okay, we're basically done. So now I've got this thing with the Gaussian elimination. I have row reduced my matrix to upper triangular. It's upper triangular, so the determinant is simply the product of the elements on that main diagonal, of 3 of which are 1. And so I'm going to now simply make that multiplication minus 25 times minus 29 over 7 minus 2/7 times 47 over 25. And miraculously, folks, I think you should stop the video and start clapping. That comes out to 117, which is the same answer as we got before. Now, it's a very different series of calculations. So using these properties of the determinant, you should recognize at this point actually a fairly laborious one to do, but you see that you can go about this in a variety of different ways, and neither one of this way I just used the full Gaussian elimination, and I got down to where I got it to an upper triangular, and then I'm done keeping track of these things that change the determinant out front. The other way I used a combination of doing some row and column operations. We don't do column operations in Gaussian elimination, and then sometimes using cofactor expansion. So there's yeah, choose wisely. Okay, it's kind of like how you want to choose your parents. Choose wisely. Okay, determinate test for invertibility. So this is an important point. A square matrix is invertible if and only if its determinant is non-zero. Okay, so if we know the determinant, we already know whether or not the matrix has an inverse. Okay, so let us just prove that to ourselves. Let B be equal to the reduced row echelon form of A. Okay, then we're going to make a statement. Det A and det B are 1, either both 0 or both non-zero. Okay, because doing row operations on A does not there's no introducing a 0. It's a minus sign if you switch rows. It's nothing if you do one row plus a multiple of the other one, and if you are multiplying through by something to get a number equal to 1, you're multiplying by a non-zero constant. So there's no way of introducing a 0. If one of them is not 0, the other one is not 0. Okay, because none of the row operations that transform A into B can introduce a 0 into the calculation. Shall I write that down? I will. Because none of the row operations that transform A into B can introduce a 0. Okay. All right, so this is one of those if and only proofs. We need to show it in both directions. So we'll assume first, we'll assume A is invertible. Then we know immediately that B, which is the reduced row echelon form of A, is I, because we have that big long theorem that we keep adding to our unifying theorem. If A is invertible, then its reduced row echelon form is I. So that means that the determinant of B is equal to 1, and the determinant of A then is not 0, and we're done. We wanted to show that the determinant, A invertible is implying that the determinant of A is not 0. Okay, let's go the other way. Assume the determinant of A is not 0. Then the determinant of B is also not 0. That implies that B does not have any 0 rows. That implies that B is equal to I, because B is a reduced row echelon form matrix, and if it doesn't have any 0 rows, the only other option is that it's I. Therefore, A is invertible. Why? Because A's its reduced row echelon form is I. Another one of the items from our unifying theorem. Okay, maybe as a memory aid to remember that invertibility and determinant not 0 mean the same thing, is you will recall when we used Cramer's rule to calculate the inverse of a matrix in this way for a 2 by 2 matrix. Like that. Okay, and you can see this here is the determinant. You can see the problem if that is 0. I mean, then we have division by 0. So sometimes, maybe if you these things go together, maybe one helps to remember the other. Okay, so we now add this new line to our unifying theorem. Okay, this keeps getting bigger and bigger and bigger. What I would do if I was you, in the morning, I would wake up and I would say to myself, okay, I've got 8 or 10 equivalent statements. How many we have as the course is going? I would attempt to list them out once every morning. And then if I couldn't, I would be like, shoot, I forgot that one. I would just look at, oh yeah, I forgot that one. And next morning, do it again. So that in your head, when you're doing some problem, what will happen then is you will realize, oh, my matrix only has the trivial solution. The system AX equals 0 has only the trivial solution. Immediately, then you write down the determinant is not 0. So these things will then come to you quickly, making it faster to solve problems. So certainly you want to have this thing in your head. Okay. Here's actually, I think, one of the more amazing things in the course. If we have a determinant of a product, that is then the product of the determinants. I mean, when you think about this, is actually quite amazing, because A times B is a complicated operation. You know, first row into the first column plus, yeah, etc. You know how matrix multiplication is complicated. Finding the determinant, if you think of, like, for example, the cofactor thing, you know, also requires many operations combining the numbers, and then the fact that there's this simple relationship between these two is quite interesting. Okay, so let's just let me just show you an example of this. That's all. I'm not going to prove this. So let me just take a lower triangular matrix like that: 1, 0, 0, 2, 1, 0, and minus 1, 1, 2. And I'll take also a upper triangular matrix looking like this: 1, 2, 4, 0, minus 1, 1, 0, 0, 2. I'll multiply those two guys together. And I got this one. That you might want to check me, but when I multiplied those two matrices together, I got this. Now, I could ask, and I will ask, what is the determinant of AB? Now, if I knew that, if I knew what A and B were, like if I just get given this, I'm like, okay, I have to start with some sort of a method. But however, if I know that this AB is the product of these two matrices A and B, and I know what they are, then it's really easy for me to do this, because this is simply the determinant of A times the determinant of B, and those are easy to calculate. That is 2 times minus 2, so it's minus 4. Okay, so it's really powerful to take, if you have a matrix and you're able to factor it into an upper and a lower triangular, then you can quickly after that find the determinant. Okay, what is the determinant of A to the power n? This is easy to see. The determinant of, we just did this, AB is equal to that A times that B. Okay, so let me just replace B with A. That tells me that the determinant of A times A is the determinant of A times the determinant of A, which is the determinant of A squared. I mean, so you just keep going like this. So that's then determinant of A to the n is equal to the determinant of A. Those brackets, man, they matter, like that. Okay, similarly, we can establish a relationship between a matrix determinant and the determinant of its inverse. So let us just take a look at how we could easily come up with that. The determinant, let us consider this, the determinant of A times A inverse, that is the determinant of I, which we know is 1. Also, the determinant of A times A inverse is the determinant of A times the determinant of A to the minus 1. And that, so those two things are equal. So that is equal to 1. So that means the determinant of A inverse is 1 over the determinant of A. Okay, things are all working nice with products. Please be aware of this. You cannot, this is not true. Okay, if you take the determinant of a sum, it's not equal to the sum of the determinants. Okay, I'm just going to show this with one counterexample. Do not do this. Okay, so here's A. Mercifully doing this with 2 by 2 examples, so it's not hard to calculate the determinants. Here's B. Okay, here's A plus B. 5, 6, 2, 1, minus 3. Minus 2 plus, yeah, minus 3. Okay, so we've got determinant of A plus B. That is going to be minus 15 minus 6, which is minus 21. Minus 15 minus 6. Okay, I've sort of sensed that horrible feeling going off that I've made some sort of small mistake, but it doesn't look like it. Okay, let's hope not. The determinant of A is 1 times minus 1 minus 2 times 3, that is minus 7. The determinant of B is 4 times minus 2, which is minus 8, minus 3, so that'd be plus 3. So that's going to be minus 5. Okay, good. It didn't work, right? So the determinant of A plus the determinant of B would be minus 12, and that is not minus 21. Okay, so that plus that does not equal that. Okay, it's not true. It's just not true. Don't do that. Okay, so just a caution there. Okay, that is all for this section. I will be back shortly with the next section. Thank you. Bye.